for time, I'll go ahead and give you the answer to these two, and then I'll put two more up so we can get some practice. Think about what we did last week. Okay, if we look here, this is our diene, right? We've got a double bond species. It's in the S-cis formation, right? That means that that's in the right formation for it to do a Diels-Alder reaction. So when I see a diene and I see a dienophile, right, that means that I've got a Diels-Alder setup. I know this is a dienophile because I have the pi system, right, the alkene, and then I have two electron withdrawing groups, right? The electron withdrawing groups changes my molecular orbitals so that I have the right energy difference here. So what I'm going to be doing, and you can't see yellow, so let's do something more transparent. Let's do flaming pink, right? So we're going to be making a bond between these two. If we look at our orbitals, right, these electrons are going to go here, make a bond. These electrons are going to go up. Those electrons go over, follow all of my electrons. I'm going to end up with a 6-membered ring. I'm turning 2 pi bonds into sigma bonds. I'm moving a pi double bond right there. And then if this is cis here, the dienophile is cis, what does that mean about my product? It's also going to be cis, right? So therefore, I want to put my 2 esters on here. They can go either up or down, right? There's not a bicyclic here, so there's not going to be a distinguishing characteristics between these two. But there I have them both up. You could have drawn them both down. It was actually the same molecule because this happens to be a meso compound. How do I know it's a meso compound? I have chiral centers, but the molecule has a plane of symmetry, so I can dissect the molecule right down the middle, or bisect the molecule right down the middle. I'm not going to pull out a knife and try and take apart the atoms, but I can bisect the molecule right down the middle to give me the same molecule. So this is a meso compound. All right, questions about this one? Okay, this type of question for a quiz or an exam is there so you will understand what trait of Diels-Alder reactions. That the geometry of the dienophile is retained in the product, right? So there's several different regioselective and stereoselective things in a Diels-Alder. This is the retention of the dienophile geometry. Okay, and the second one, this one's a little bit different. They had some like this in your book. I don't think I assigned any on Chem, but what we're doing here is actually retro. What two groups, what diene and what dienophile will it take to make this? And these are easier than they might look at the beginning, right? What you can think about is if this double bond is here, right? If we go across this double bond and break it here and here, this is going to be my structure, right? So therefore I can take that, and this is a common question, is to figure out how you came up with a Diels-Alder product. So I broke above and below straight across from my double bond. And then on the other side, I've got my double bond, but now I need to figure out the geometry of my starting material. And in this case, since it's trans, I want to put my 2 groups trans on that double bond, okay? So again, go wherever the double bond is in the 6-member ring, directly across from that. Then you're going to break the bond above. You're going to break the bond below. That's going to be the separation between your diene and your dienophile, right? So that's how I got this one. Then over here, I need to look at my geometry. My geometry is retained. So if this is trans, this has to be trans. Okay. Let's try a couple more. One related to Diels-Alder, one related to the first reactions in the chapter. We'll take a little more time on this one. So give me the products of this one. And give me the product of this one. Okay, let's go ahead and take a look at this one. That was just a minute, so it was somewhat quick. Remember, on a test, you're going to have, or I haven't told you this, so new information for the test. So we usually have about 25 or 30 questions, which means in a 75-minute class, you're going to have a good 2.5 to 3 minutes, right? So you'll have anywhere between 2 and 3, depending on difficulty. So that was just a minute. So if you're able to answer one of these, that's great. If you're able to answer both of them, you're doing fantastic. Okay. So the first one, okay, again, here's our diene. So what I'm going to do is I'm going to draw my dotted lines here. That gives me a place to think about where I'm going to draw my new sigma bonds. I always like to draw the mechanism, right, to show me where I'm going to put those bonds. Now, if you notice, I have a ring system to start with in my diene. That's going to mean that I have a bicyclic. If I have a ring system in my dienophile, that's less important. That will not mean that I have a bicyclic. So here I'm going to have a bicyclic. So I'm going to put this up. And then these are the two new bonds. And let's go ahead and put them in a different, slightly different color. While we're learning, we can use some tricks. Okay. And then here, and then I'm going to put this down. Right. And so that's going to fold over, and to make sure I get it right, I need to put that double bond in my 6-membered ring. So if I look at my structure here, here's my starting structure, right? So 1, 2, 3, 4, 5. Here is the other side, this cyclic, right? So 1, 2, 3, 4. I've made a new bond here and here, right? That goes to my 2 and my 5 position. And I've shown this in what formation? Why did I show it down? This is one of those stereo selective. The pi bond here is going to overlap with the pi bonds back here, right? And so this is known as endo, right? So this is the endo structure. And showing that down is the endo. This is most obvious in bicyclics, right? So whenever you have a bicyclic, one of the things that I'll be looking for is, do you know that the endo is favored over the exo? The exo would be up. The endo is under, it's folding. The pi bonds are overlapping. That's giving me a more stable transition state. That more stable transition state is what ends up giving me endo versus the exo, right? I'm inside the envelope versus outside the envelope. Okay, questions about this one? Yes, ma'am. Endo, yes. The transition state is always folded under. And so therefore, endo, even in the previous one, endo was the favored transition state. It just didn't show up because it wasn't bicyclic. Okay, if we look at the next one, this one, let's go ahead and look at the mechanism. So we get, either one of the double bonds, this is symmetric. So I'm going to end up giving the carbocation here, right, with the hydrogen here. Let's fix that a little bit. Okay, got the positive here. Then this can give me a resonance structure to show this. Okay, and each of those will go give me a bromide. So let's pick a different color. So we're going to add the bromine to one and then bromine to the other. And so my two possible products here will be the bromine in the middle, this one, and then the bromine towards the end. So that was the last chapter, right? So that was the Thursday before last week, and then Tuesday and Thursday. The paracyclics that we covered on Thursday, it's good to be aware of those, but those aren't going to be a high point. If you noticed on the learning objectives, they're not listed extensively. So understanding the paracyclics and how paracyclics are there important. If you get to grad school in organic chemistry and they ask you, like I did, that, I've never seen those before in my life. And then they'll tell you, you went to a horrible university, and the University of Oklahoma is not a horrible university. So therefore we must cover paracyclics. So we did. The focus will be on the Thursday, the first Thursday, and then last Tuesday's lecture. Okay, the paracyclics will be important if you go on to advanced science. Even in some biochemistry, paracyclic reactions will be important, but of course, organic. Today, we're going to move into aromatic compounds. And that doesn't mean essential oils, although essential oils sometimes have aromatics. Aromatic compounds are most often given by benzene. It's the characteristic aromatic compound. Now, historically, they were called aromatics because they did usually have an odor, sometimes pleasant, sometimes not, most often decently pleasant. But they had more odor to them, or they could be picked up at a higher degree by chemists than acyclics or other cyclics. So the origin is that they were aromatic, but that's not why we call them aromatic now. Why we call them aromatic now is because of this ring system and the fact that we have these electrons, and we'll get more in depth today, that, remember, if we look at the lowest energy level, when we look at these pi bonds, right, what we're going to do is we're going to get a full overlap and communication. That was ugly. Communication between all these pi bonds. So these double bonds aren't acting like they're separate. This whole ring is acting like an electron ring, right? And because of that, there's several things that occur. Aromatics are more stable than other pi systems. So if I can make something aromatic, it's going to be more stable. That also means that whenever I react with aromatics, I need to increase my reactivity. So they're more stable, which means I need stronger reagents. So you'll see that some of our reagents, when we get into the last chapter and last section of this chapter 17, and then next chapter, chapter 18, you'll see that they seem to be similar to our alkene and alkyne reactions, but they're slightly different. That slightly different is because of the stability of the aromaticity. The other thing that the aromaticity does, and this is important, we're not going to get involved heavily in organic chemistry, but at one time they thought aromatics were just a convenient way to make flat molecules because it's planar, right? I've got 6 sp2 carbons, it's 120 degrees. This ring is perfectly flat. I can put 5s and 6s together, aromatic, and I can make them all flat. So I can have these big flat systems. Our base pairs in DNA are aromatic systems, and they're flat, right? But it turns out that is important, but that's not the only reason. It turns out because of this pi system, you can get through space interactions. So you can think about it, I got these electrons going here, and just like in one of the Marvel movies, right? It's because of that circle of electrons, it has electron density going in and out of it, which means that you can get communication not only through the ring system, but to the sides, above and below the ring system, or above and below, if you look this way, or this way, which means I can actually transport electron density through space in aromatic molecules, right? And so that turns out that there are attractions that we can't describe in biological systems just based on the hydrogen bonding. And these interactions have to do with electron-rich pi systems, aromatic pi systems, and electron-poor aromatic pi systems. So what you do is you sometimes will see stacked pi systems that are attracted, and that's why the bonding energy is high, right? So the aromatics you'll see quite a bit in biological systems, and there's a few reasons why you see aromatics. One, they're really stable. 2, they're flat, which is kind of nice. If you need a spacer, you get a big flat spacer. But they also not only can go through the bond or through the pi system, they can go through space when they communicate electron density, right? And so those 3 things can add to this, all right? Now we're starting in a new class, so let's start with nomenclature. Okay, because we're going to a ring system, we're not going to be using the same parent names, right? So when we look at benzene, this is our main parent name, benzene. If we put two of these together, we get naphthalene. But we also can then have a set of names based on the substituents. So these are so common that there is a group of base names based on the substituents. So if I put a CH3 on here, this is known as toluene. Right? It could be known as methylbenzene, but its common name, toluene, is an accepted parent name. Because of this, there's a list of these that you're going to need to know. And we'll go through that list now. If we add an OH to it, this is one that you'll see a lot in biological systems. This is phenol. Not as common unless you're in fragrance chemistry, but anisole. Aniline. So an NH2 group attached is aniline. Put a benzoic acid up here, or sorry, this is benzoic acid, but put a carboxylic acid on it. Benzoic acid. This is a common one. If you've had a soda today, there's a high chance that you had sodium benzoate. Sodium benzoate is just the sodium salt of benzoic acid. You'll see sodium benzoate as a stabilizer in lots of manufactured goods. Right? Now I'm just turning them sideways, but they're the same attachments. This one is benzaldehyde. Hey, benzaldehyde is, how many people like maraschino cherries? The red cherries that you put on sundaes, right? Okay, they have a unique flavor. It turns out that flavor is not cherry flavored. It actually turns out it's essence of almond, and the essence of almond is actually benzaldehyde. And at one time, you actually had to squeeze the almonds to get the oil out of it and purify it. But turns out benzaldehyde is really easy to make, so now it's easy to flavor anything you want with artificial almond flavor. So benzaldehyde. Acetophenone. And the last one that we'll cover in this section is styrene. And if you polymerize styrene, you get polystyrene. Okay, so you need to know these common names because they're also accepted parent names. So toluene, phenol, anisole, aniline, benzoic acid, benzaldehyde, acetophenone, and styrene. You can also have benzenes attached to something. So if I had a big long chain like this, instead of naming it as a big long chain and the benzene, I'm going to name it as a big long chain with the psi group. The psi group is known as phenyl. So this would be one. So this would be 2-phenyl heptane. Okay, if I add an extra carbon here, this is known as benzyl. So without the carbon, right, directly attached to the benzene, it's a phenyl. When you add a carbon, that's a benzyl. We've seen this benzylic bromination when we use NBS, right? That was from last chapter. We'll see it quite a bit in this chapter. We'll use that phrase benzylic. You can also then have things that don't have parent names. Let's say like your halides. So with the chloro, this would be chlorobenzene. If I can spell it right. Do I need the number? No. It's going to be 1, but you don't need to add it because it'll always be 1. Right? So here, this is bromo, benzene. So for the ones, the mono substituted that don't have a parent name, you just use benzene as your parent name and add, so propyl, benzene. Questions about these? And I'll post all of these online after class. Okay. For dye substituted, you can use a simple numbering system for this, or you can use a new set of arrangements. And it turns out those arrangements, regiochemistry is pretty prevalent, especially in biology. So we'll go through those. So if we look at this one, this is called ortho, from the Latin for next to, right? This is meta, which I think means alongside, and then para, right, is opposite. So we see ortho, meta, para. Turns out that this 2-methyl group can also be known as xylene. So this can be known as ortho-xylene, right, or O-xylene. I can also call it 1,2-dimethyl benzene. All 3 of those are acceptable names. Oh. All right. Then meta. So metaxylene, M-xylene, right? And then 1,3 dimethyl benzene, paraxylene, P-xylene, and 1,4. The ortho, meta, and para works really well with dye substituted, but after that, it really falls down. So it really only has one place. It's almost like cis and trans versus E and Z. Cis and trans works well when you have a di-substituted alkene, or if you have a di-substituted system on a ring. But after that, it really falls apart. Same thing here. Orthometapair works for this. Mixing these can be difficult and is usually not done. You might find a really, really old bottle of something that says orthochlorometabromophenols. They don't do that anymore. Okay, so really this works just for the di-substituted. Okay, so let's name a few to see if we can name these correctly. We're going to find a parent name, right? And then we're going to use the meta. And then I'd like you to go ahead and use the benzene as the parent name and the second one with the number. So we're going to get 2 names for each one of these. So let's take a little time. Find one where you use one of the parent names that we looked at previously. The other name it off of the benzene using numbers. Okay, let's do the first one and then I'll give you a little bit of time for the second. So the first one, if we look at this, I've got an OH and I've got a methyl. Now I have 2 potential parent names, right? I have phenol, right? And I have what? Toluene. Now, what do you think the preference would be? Phenol or toluene? Turns out phenol. You look at the oxidation state of your side group, so phenol would be our preference here. So this would be named as a meta methyl phenol. If I name this as a benzene, right, then I have a 1 and a 3. So let's go back in, 1 and a 3, but I also could have what? Let's pick orange, 1 and a 3. Okay, so which one comes first, the methyl or the hydroxy? The hydroxy comes first, and since 1, 3 and 1, 3 are the same, I'm going to name this one 1 hydroxy, right? That's the alcohol side group name, hydroxy. 3 methyl benzene. Usually if you see chemical bottles now, you usually will see this name. This name is a little bit better because usually chemicals now are sold internationally. And so the IUPAC name, the full IUPAC name is used internationally by chemists. The common names may or may not be used in certain countries, especially depending on their lettering system. The metamethyl phenol, that's what you would see in a biology lab most often. Okay, the common names are preferenced in many cases. Okay, if we look at the next one, now we don't have to, right? We got the ethyl group. We don't know what the side group name is there, so we can use the toluene. So I'm going to have toluene. let me use the same color. So the darker blue. So toluene. And now I have an ethyl group. Right, and I'm going to have that also on the meta. This time I'm just putting the M. You'll sometimes see these drawn with a line underneath. It's just because the meta and the M are almost always italicized. Okay. So when you see these in print, they'll be italicized. If we name it the other way, now we got an ethyl and a methyl. Again, we have a 1,2 and a 1,3. The ethyl comes before the methyl. So I'm going to have 1 ethyl, 3 methyl benzene. Okay. Let's take a little bit longer on the last one. Feel free to go back and look at your parent names. Okay, so we can lose aniline is going to be the parent name here. So the nitrogen, the NH3. This side group is known as a nitro group. So NO2 is nitro. So this is going to be para, nitro, aniline. Turns out the para-nitroaniline has a bright yellow color to it because of the push and pull. Turns out the amine, the NH2 is a donated electron donating group, and the nitro group is an electron withdrawing group. So that push and pull actually gives me a dynamic color. So it's really intense. So para-nitroaniline, and then if I name this as a just a benzene, this is going to be 1 amino. That's the side group for the NH2. Amino 4 nitro benzene. And I didn't do my colors correctly there, but hopefully you understand. Okay. Yeah. You look at the alphabetic. So if you're 1 and 4, 1 and 3 are both the same both ways, you go with the alphabetic. So the amino comes before the nitro, so I give the 1 to the amino. All right. So what happens if we have polysubstituted? Okay, we're going to find a parent name. We're going to name our substituents. Going to assign a locations. And then we're going to arrange alphabetically. So for this one, we've got the hydroxy group, the bromide and the chloride. Do we have a parent name with the hydroxy? Right, we can use phenol. So we can use our phenol. If we use phenol, that means this needs to become the 1 position. Right. My other substituents going to step 2 is bromo and chloro. Get my R's and my O's backwards. Chloro. So if we go 1, 2, 3, 4, 5, 6. Go the opposite direction. So counterclockwise, 1, 2, 3, 4, 5, 6. Which number system are we going to use? Are we going to use the clockwise, the purple one, or the green one on the counterclockwise? green, right? Because 2 and 5 is lower than 3 and 6. Then we put this all together. We have our phenol. Bromo comes before chloro, so we'll do chloro. Okay, that is the 2-chloro. And then the bromo. And that's the 5-bromo. So 5-bromo, 2-chlorophenol. Any questions about this one? You want about 20 of these on the test? I'll put one, maybe 2 or 3, but probably not 75% of the test. All right, let's try some of these before we move into structure and reactivity. So let's take a little time on these. This one, NH3, O2N. Let's try the first one, and then I'll give you a little more time on the second two. Okay, here we have an amine, right? Amino, and then 2 nitro groups. Do we have a parent name that has an amino in it? Yeah, we have aniline, right? So we can use aniline. That makes that a 1. So 1, 2, 3, 4, 5. If we go the counterclockwise, we get the same numbering system, right? We know these are nitros. So putting that all together, we get 3,5-dinitro aniline. Oh, yeah, it should be 2. That's what the question was. Should be a 2. I apologize. Okay, let's take a little bit more time on the next 2. On this one, we have a methyl side group, Means we can use the toluene name. We have a chloro attached. Our position here is 1, 3, or we can use meta since there's only two things two substituents. So this one can be meta chloro toluene. We could have also named it 3 toluene. No need for the 1. On the last one, do I have a parent name? Is there a parent name that has the bromo or the chloro? No. So on this one, I'm gonna have to use it as benzene, right? So my parent name here is gonna be benzene. And I've got the chloro, bromo, right? Chloro, so I'm gonna have a dichloro species. And now we can look at our numbering. Here's where it gets kind of creative. So we'll have to use all kind of colors. So we can start at the top. 1, 2, 3, 4. That's one possible numbering system. We can use the purple. 1, 2, 3, 4, 5, 6. We could use 1, 2, 3, 4, 5 for the green, or for the fuchsia color. Oh, I already used that one. The pink color, I could have 1, 3, 4, 5, 6. Or I could go 1, 3, 4. Or I could go 1, 2, 3, 4, 5. So we've got 1, 2, 4, 1, 4, 6, 1, 2, 5, 1, 3, 6. And this does seem like overkill, but one day you'll get it wrong if you don't do all of them. 1, 4, 5, and then 1, 3, 4. So what's our lowest possible numbering? It's going to be the orange ones, right? 1, 2, and the 4. So therefore, this one is going to be 2 bromo, 1, 4 dichloro benzene. I didn't leave myself enough room. Really long name. Okay. Questions about nomenclature? Okay, let's move into structures. Yeah. Para? Oh, you usually go with the higher oxidation level. So an oxygen would have a higher electronegativity than a carbon or a nitrogen. So oxygen, nitrogen, carbon. You can also do oxidation states. So carboxylic acid might be over a aldehyde, be over an alcohol. So. When we look at the structure, right, we can show it 2 different ways. And we know that what's happening, right, is that this is going to be a continuous pi system. And so sometimes, especially older textbooks, you'll see benzene drawn this way. So it's not like we have 3 double bonds and then we have a resonance structure with 3 favorable bonds, right? These are all the same. So therefore the distances between all of these are the same. So it's not behaving like 3 double bonds. It's not behaving like a triene. And it's because if we look at our pi system, right, we can phase this in a way where all of the phases of the top are aligned, right? So that we have a continuous pi system throughout this. This continuous pi system is the stability for the ring system. And it's going to be the stability that's going to drive aromaticity as a stability group in our Huckel rule, which we'll see in a second. It also means that when we look at our reactivities, we don't see the same type of reactivity that we would see with an alkene, right? So if we had an alkene and we reacted it with Br2, we would get the dibromide and an anti-addition. But if we take the aromatic and react it with bromine without any other catalyst, just in the solvent, we see no reaction. So it's just not the same as an alkene. The stability of this pi system means that we have different reactivities. Similarly, if we looked at taking a alkene, reacting that with hydrogen and something like palladium on carbon, one of our nickel, palladium, or platinum catalysts, this is going to hydrogenate that all the way. So we go to saturated. If we try that with an aromatic, it's easier to say no reaction. Right? We get no reaction. But if I take the same reagent and I up the conditions, so because of the conditions, I'm going to use nickel, 100 atmospheres. What are you sitting in right now? 1 atmosphere, right? So 100 atmospheres is a lot of pressure. And then 150 degrees Celsius, right? So high temperature. So this is what we call a bomb type reactor. Bomb not meaning explosion, but bomb meaning keeping it from exploding. So we're going to put this under high pressure. Under these conditions, right, these intense conditions, we can get this to react. And that's going to be a theme that we see with benzene reactions. Because of their aromatic stability, we're going to see the increased need for different reagents. Now, when we look at the aromatic, remember we have 6 pi electrons. So if we look at our energy chart here, turns out what happens in aromatic systems is you have a divergent energy level. Divergent just means 2 at the same level. And so when we look at our pi, our psi 2, so here's psi 1, psi 2, psi 3, this would be psi 4, psi 5. So our 2 and 3 are divergent, same energy level. Our 4 and 5 are both the same energy level. When we fill in our electrons, we have 6 pi electrons. What we see is that we fill up these electrons. The psi 1, right, this one right here, if we go back up to this drawing that I drew here, this is the psi 1, right? So this is what I was talking about, having them all in the same phase. If we think about psi 2 and psi 3, these both have one node, and there's 2 different ways to get one node. That's why there's divergent energy levels. Now, to get this energy level, right, where we have full homo divergent energy levels, what I want is I want an odd number of electrons. And it turns out that this can be turned into Huckel's rule, or is Huckel's rule. Which for aromaticity, I'm looking for 4n plus 2 pi electrons. And please correct this because it should be pairs. So odd number of electron pair. So if we look at Huckel's rule, if n equaled 0, then Huckel's pi electrons would be what? Well, 4 times 0 would be 0, then 2 pi electrons, right? So 2 pi electrons. How many pair? 1 pair, right? So an odd pair. If we had n equals 1, how many electrons are we going to get there? Well, if 4 times n is 1, then that gives us 4 plus 2, that gives us 6 pi electrons, right? Or 3 pairs, right? Again, odd. N equals 2. So Huckel's rule, a lot of people get confused about this. All it is a way for us to get the number of electrons, right? The pi electrons. And so n can be anything. N is not the number of electrons. N is just an integer. It could be 0, it could be 1, it could be 2, it could be 3, it could be 4. And it gives us a series, right? So here, if n is equal to 2, 4 times 2 is going to be 8, plus 2 is 10 pi electrons, right? Which is 5 pairs, again, odd. If n equaled 3, 3 times 4 would be 12, so that's 14, right? So it's just giving us a series of electrons. When we look at those, my Siri just popped up on my phone. So series, not Siri. So series of electrons. Okay. So Huckel's rule is important to aromaticity. So aromaticity is this stability that we're looking for, right? And what we want is we want a cyclic pi electron system. It needs to be continuous, which means it needs to be planar. If it's not planar, then it can't be continuous. So if my electrons aren't lined up, right, if they go like this, then I'm not going to have a continuous pi system. So you got to watch for planarity in my molecule. And then the third one is I need Huckel's number of electrons. Okay, so there's several ways that I can break up aromaticity. I could not have a cyclic pi system, right? So if it's not in a cycle, if it's not in a ring, then I'm not going to have a cyclic system. That's not going to be aromatic. I could not have it continuous. If I put an sp3 carbon in the middle of the ring, that's not going to be a big continuous pi system. And I should say pi electrons, right? So continuous pi electrons. The ring could be so big that it's no longer planar, right? So if I have really big rings like 10 and 12, is that going to be able to be planar? No, it's probably going to flux out of it. And actually turns out that 8 carbons is enough for it not to be planar. Yes, sir, you have a question? I can't hear you. The n is an integer. It can be any integer. So just pick one. Pick an integer between 0 and whatever. Yeah, right now. 5. So 5, n is 5. So therefore, if I put that in the formula up here, 4 times 5 is 20 plus 2, which gives me 22 pi electrons. So I'd have 22 pi electrons. If I had a molecule that had 22 pi electrons and it was cyclic and it was continuous, that could be an aromatic molecule, right? So any integer works. All it's giving you is a series of a number of electrons, right? If it doesn't meet this series, which is 2, 6, 10, so it's a scientist's way of not saying 2, 6, 4, 10, 14, 18, 22, 26, 30, right? They're giving you a formula. And that formula works. All you have to do is, as long as that you can find an N that matches that. Now, if it came up with 20 electrons, right, there's no way for me to have a whole number N and come up with 20 electrons with 4N plus 2 pi electrons. So what you can do is the N doesn't identify anything. The N is just an abstract whole integer, right? But what the N does is tell you which Huckel electrons, right? Which number of electrons match the Huckel's rule, right? Okay, so if you had 32 electrons, what you could do is, what N would get me close to 32? I don't know. 4 times 6 would be 24. That's not enough. So 7, that would give me to 28. But if I add 2, that gives me to 32. If I go to 8, all of a sudden that gives me to 32 plus 2, that's 34. So therefore 32 pi electrons does not meet Huckel's rule, right? So the N doesn't, it's just a whole number integer, right? Okay, so these are my 3 rules. If I have these, it's aromatic. If I break these, there's a couple of different ways I could break it. I could have a non-cyclic pi system. A non-cyclic pi system is non-aromatic. If I don't have a continuous pi system, it's non-aromatic. But if I have a forced continuous pi system, and I'm putting forced in there for a reason, then if I don't meet Huckel's rule, if I'm off 2 electrons, then that is anti-aromatic, okay? So aromatic has to meet this. If 1 and 2 are broken, right, then that is going to be non-aromatic. And non-aromatic is just as stable as any non-aromatic, right? It's not any worse. But if I end up with not Huckel's rule, but 4n pi electrons, right, then that is anti-aromatic. So if aromatic is much more stable than a standard species, what would you expect for anti-aromatic? Much more unstable. So do things want to be anti-aromatic? Absolutely not. So therefore, there are some reactions that do not occur because if they occurred, they would create an anti-aromatic species. All right, let's try a few of these. We know benzene, so let's start there. Non. Sorry, I should probably put non-aromatic is what I put, but non-aromatic is probably more correct. So anti-aromatic, non-aromatic, aromatic. So if we look at benzene, how many pi electrons do I have? Well, I have 6 pi electrons, right? Does 6 pi electrons match Huckel's rule? Yes, right? Right. Yes. Is it a continuous cyclic pi system? So that's 1 and 2, continuous cyclic pi system. Yes, it is planar. Right. So since all 3 of these are the same, right? Continuous, cyclic, and 6 pi electrons, then this is aromatic. Okay, let's look at these 2. Do we have cyclic pi system in the first one? Can I draw continuous, or can I draw sp2s all the way through here? All of these are sp2s. That means every one of these has a p orbital on it. Is it planar? What would I have? A 6-membered ring made of 120-degree angles. Would that be planar? Yes. What would I have if I had another 6-membered ring right next to it made of 120-degree angles? Would that be planar? Yes. So it is cyclic. It is a planar. Right? It's a planar structure. And then what is my number of pi electrons? Well, I have 2, 4, 6, 8, 10. So I have 10. Oh, that's not 10. I have 10 pi electrons. So is 10 pi electrons part of the Huckel rule? Yes. If I had n equal to, again, n could be anything, I would end up with 10 pi electrons, right? So therefore, this one is aromatic. Okay, on the next one, do I have a continuous pi system? Or do I have a pi system? Is every single carbon sp2 with a p orbital? Yes. So I have a cyclic pi system. Is it continuous? No. Well, why? Well, think about this. Now I've got 120 degrees, but in 8, can I get 120-degree angles in an 8-member ring, an octagon? No, an octagon has much smaller angles than that, right? So now what happens is that this molecule is not sitting flat. It actually looks like a box that you sat on. Right? So if we look at it, it kind of looks like a box that's kind of furled out. So imagine a perfectly square box and you sit on it and it kind of goes, boom, right? And the bottom flares out. That's what we have. We have this kind of shape like this. Now, if it's doing like this, what's going to happen to my orbitals here, right? So I got my P's here, P here, but what are these? Right? Are those going to be aligned up with the ones in the bottom? No, right? So therefore, not continuous. It's not planar. So this one is non-aromatic. Because it's non-continuous. If this one had been planar, would it have been aromatic? 2, 4, 6, 8. 8 electrons. Does that fit Huckel's rule? No. So if I could force this one to be planar, it wouldn't be aromatic. It would have been anti-aromatic, right? But if you don't have a cyclic system, or if you don't have a continuous pi system, that is non-aromatic. You don't have to worry about counting your electrons. Okay. We've got time for a few more. So now let's look at some different charged ones. Okay, y'all take a look at these, spend a little time. Feel free to talk to your neighbor if you're wearing a mask. Let me know if they are aromatic, non-aromatic, right, or anti-aromatic. Okay, let's take a look at the first one. Give you a little bit more time on the next two. On the first one, do I have a continuous pi system? Well, there's two parts of that, right? Do I have p orbitals? And I do have p orbitals on each one of these, right? The carbocation would have a p orbital, right? Is 5-member rings with sp2 potentially planar? Planar enough, right? Planar enough, 5s and 6s. 6s are perfectly planar, 5s are close, right? So this would be continuous, but how many pi electrons do I have? I have 4 pi electrons, right? So with 4 pi electrons, does this match the Huggles rule? No, it is got a continuous pi system, right? Cyclic pi system, but it has the wrong number of Huggles electrons. So therefore, what is this? Anti-aromatic. Which means forming this, right, would be difficult. It has a p orbital, but it has no electrons, so therefore it doesn't add to the electron count. Right? So it gives me a continuous orbital system, but it doesn't give me any more electrons, so I end up with 4. Okay. All right, let's take a look at the next one. Let's take a look at the other two, kind of walk through it the same way. Normally when we think about anions, right? So normally when we think about anions, what would we have said that orbital was? We would have said it was sp3, right? But as electrons and not bonded species, does it have to be sp3? Could it be sp2? Yes, it could hybridize to be sp2 if it was advantageous to hybridize to be sp2. If I had atoms connected there, there would be nothing I could do. It would have to be sp3. But here, could it be sp2? Yes. So I could have this as an sp2. So therefore, does this have a continuous pi system? Yes, it has a continuous cyclic pi system, right? How many electrons are in the negative? 1 or 2? I've got 2 electrons, right, are going to be in one of these p orbitals. So I can draw it like this, right? Now, how many electrons do I have in my p orbital? I have 6 pi electrons. So 6 pi electrons, what is is this match Huggles? Yes, 6 pi electrons match. This one is aromatic. Now, what assumption did I have to make to say that this was aromatic? I had to say that something that I might have thought was sp3 was sp2. Since it's electrons, is there any problem with it rehybridizing? No. Does it want to rehybridize? Hell yes. Why? Because if it rehybridizes, then it becomes aromatic. And if it becomes aromatic, it becomes more stable. We all want to go to low energy, right? Okay. So a lower energy state is a comfortable state. It is not unnatural to want to sit on your behind all day on Saturdays, right? It's not unhealthy, but it's not unnatural to want to do that, right? So the next one, let's take a quick look at that one. Now, instead of that electrons, I have 2 hydrogens, right? Can I do anything with this sp3? No. So therefore, this is not continuous. This is non-aromatic. Okay, and that is our time. So we'll start here in the middle of chapter 17. On Thursday, we'll finish chapter 17 and probably start chapter 18. I will have homework up later today on 16. You'll have a week to do that. It will be focused over Diels-Alder and reactions with multiple bond systems, okay? Less on the paracyclics. We'll see y'all next time. Have a good day.